Hello there, Mr. Sutton here, bringing you the AB Calculus 513 Extra Practice Number 3 solutions on average value. To find the average value of this function over this interval, we're going to do 1 over the interval length, so 1 over 3 minus 2, times the integral from 2 to 3 of the function they have up here, 5 times x to the negative 1, or 5 over x dx. All right, so this is really just 1 over 1, which is just 1. Here, the antiderivative of 5 over x, that's going to be 5 ln absolute value of x, evaluated from 3 to 2. I'm going to yank this 5 out of there, and inside of parentheses, I'm going to have ln of 3 minus ln of 2. So let's see here. I can actually combine these if I wanted to. I mean, I've got all constants, so technically I'm done. But if I combine these using my log rules, this is really ln of 3 over 2, and we still have a 5 out there. So this is what a simplified answer could look like. To find the average value of this function, we're going to do 1 over the interval length, so 1 over pi over 2 minus pi over 4, times the integral from pi over 4 to pi over 2. And then our integrand is just going to be the function we're taking the average value of, negative 2 cosecant squared of x. All right, so this is going to be, let's see here, this is really 2 pi over 4 minus pi over 4. So this is 1 over just pi over 4. And my antiderivative here, this is going to be, let's see here, 2 cotan of x, evaluated from pi over 4 to pi over 2. So let's see here, I can flip this thing to write 4 over pi. And we've also got a 2 here that I can multiply by the 4, so that gives me the 8 over pi that I see here. And inside, I've got the cotan of pi over 2 minus cotan of pi over 4. All right, well, what does all this come out to? So we still have the pi over 8 out there. Cotan of pi over 2, well, that's really 1 over tangent of pi over 2. But that's a little bit tricky because tan of pi over 2 is undefined. Let's think about this as cosine of pi over 2 over sine of pi over 2. Well, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this is really 0 right here. And then cotan of pi over 4, well, this is the reciprocal of tan of pi over 4, which is just 1. So the reciprocal of 1 is just 1. So we're really just subtracting 1 here. So when all is said and done, this ends up being negative 8 over pi. For this one, finding the average value of this, I need to do 1 over the interval length, so that's 1 over 5 minus 2, times the integral from 2 to 5 of negative 2 over x cubed dx. So I'm going to rewrite this as negative 2x to the negative 3 because I'm about to take an antiderivative, so that'll make it a little easier. We have a 1 over 3 on the outside there, and for my antiderivative, I've got, let's see here, this bumps up to a negative 2. Dividing by negative 2, that actually cancels out this negative 2. We're left with just x to the negative 2 inside, still evaluating from 2 to 5. So I've got a 1/3 times, and now I'll just put all this in a parentheses. This is going to be 1 over 5 squared minus 1 over 2 squared. So this is 1 over 25 minus 1 over 4. So we need a common denominator here. I think 100 will do the job. So this is 4 hundredths minus, let's see here, this is going to be 25 hundredths. That's going to be negative 21 over 100 inside there. And if I really want to keep simplifying, I mean, I could have just stopped here when I had all constants. But if we keep going, the 3 and the 21 can cancel a little bit, leaving me with just a 7 up there. So this ends up being negative 7 hundredths. On this problem, which is a calculator-based problem, I'm trying to find the average value of this function over the interval from negative 2 to 1. So since it's a calculator problem, the setup is really everything on this. So I'm going to do 1 over the interval length, so 1 over 1 minus negative 2, or 1 over 1 plus 2, if you want to write it that way. Either way, we're multiplying this by the integral from negative 2 to 1 of all this stuff. Now, since they already defined this as f of x, I'm just going to write f of x dx in here, and they know what I mean. So let me go in my calculator and do this now. So here I am in my calculator in my y equals, where I've entered this f of x function. And I'm going to quit out of there, and I'm going to do, let's see here, this is really 1 over 3. So let me do alpha y equals, do my fancy fraction mode to get exactly 1/3 out of that. And now I'm going to do math 9 to get my integral from, we're going from -2 to 1. And I'm going to put y1 in there because that's where I stored f of x. So alpha trace and pull up y1, put a x for the dx, press enter, and all that comes out to, hey, exactly 0.05. Well, that's neat. So there we are. To find the average value of this function, we're going to do 1 over the interval length. So that's 1 over radical 3 over 2 minus radical 2 over 2 times the integral from root 2 over 2 to root 3 over 2 of, well, f of x here. Not going to bother rewriting it because I already know what f of x is. So we'll just write f of x dx in there. And now I'll do this whole thing on the calculator. The very first thing I'm going to do is to enter this f of x function in my y1, just so I don't have to mess around trying to put this in the integral form. And then let me get out of there. And I'm going to be setting up a big fancy fraction here. We're going to do, let's see, alpha y equals n over d. And then let me put a 1 on top, and down below we're going to do another fancy fraction. This one's going to have radical 3 over 2. And then I'm going to be subtracting fancy fraction, radical 2 over 2. So that's the bulk of the time on this problem, is just setting that up. And now we're going to multiply that by Math 9 integral from, well, let's see here. We've got radical 2 over 2. So radical 2 divided by 2. And up here we've got radical 3 over 2. There we go. Divided by 2. Whoop, go back. There we go. And now in here, I'll save a little bit of time. We're doing alpha trace to pull up my y menu, y1. Plug that in there, put an x in there for dx, press enter, and hope for the best. Comes out to about 1.647 if I round that off. And this one's done. On this problem, I'm given this f of x function, and I want to find the average value of f over the interval from 1 to 7. So to do this, we're just going to do 1 over the interval length, so 1 over 7 minus 1, times the integral from 1 to 7 of, well, whatever you're trying to average, which in this case is this f of x function. So I'm just going to write f of x dx in there. Let me do this on my calculator now. If you look at the answer choices, that's what's required here. So here I am in the y equals. In y1, I've put my f of x function. Quitting out of there now. Let me do, let's see here, fancy fraction. We're going to do 1 over 6. And then math 6 to get my integral. We're going from 1 to 7. And in my integral, I'm going to do alpha trace y1 to pull up that function I just entered, dx, and press enter. We got about negative 2.461, which gives us choice B. For this one, we have the graph of a continuous function f, and we want to know the average value of f on the interval from -2 to 8. So for this, I'm going to do 1 over the interval length, so that's going to be 1 over 8 minus -2, times the integral from -2 to 8 of whatever I'm trying to average, in this case, f of x, dx. All right, so this is going to be 1 over 10. And now to find this integral, you actually just have to take the area under this curve from -2 to 8. So this is going to consist of 2 triangle areas. Our first triangle, we're doing 1/2 base times height. So in this case, that's 1/2 times a base of 6 times a height of 5. And then we have this other triangle right here from 4 to 8. So that's 1/2 times a base of 4 times a height of 4. So inside this bracket parentheses now, half of 6 is 3 times 5 is 15. Over here we've got 8. 15 plus 8 gives me 23. And 1/10 of 23, basically 23 divided by 10, is going to give us 2.3. Just move the decimal. So that ends up being answer choice C. For this one, they're telling us that the average value of some function f on the interval 2 to 6 is 3. So they're giving us the average value. Based off that, they want the value of this other integral. Okay, well, let's set up an equation with the information they gave us, and hopefully we'll get something useful out of that that'll help us decipher this other thing they threw at us. So if the average value of f on this interval is 3, then we can say that 1 over the interval length, so 1 over 6 minus 2, times the integral from 2 to 6 of f of x dx, this is the average value of f of x, by the way, we can say that this is equal to 3. And just multiplying both sides by the 4 that we get down here, we can say that the integral from 2 to 6 of f of x equals 12. So that might be helpful, because I see that I have an integral here from 2 to 6 with an f of x involved in it. So if I know what just the integral from 2 to 6 of f of x by itself is, maybe that'll help me piece together this larger integral. So let's take this integral now and use some of our definite integral rules to sort of split this thing up and break it down. Because I'm adding two things inside this integral, I can actually split this into two separate integrals. And in my first one, I can actually pop this 5 outside as a constant multiplier. So I can rewrite this whole thing as 5 times the integral from 2 to 6 of f of x dx. So I'm just rewriting this original now, plus integral from 2 to 6 of 2 dx. And now if I take each of these things individually, well, we just saw up here that the integral from 2 to 6 of f of x dx, this thing basically, is 12. So this is really 5 times 12. And over here, if I'm taking the integral from 2 to 6 of 2, basically finding the area under the horizontal line y equals 2, this is going to be a rectangle. The base is just going to be the interval length of 4. Height is going to be 2. So basically 4 times 2 for that integral. So this is going to be 60 plus 8, or 68, giving me answer choice D. For this problem, we're given this polynomial for f of x, and we want to know for how many values of x in the interval from 0 to 1.565, which is kind of random. We want to know for how many values is the IROC of f equal to the AROC on that closed interval. Okay, so at some point we need to figure out the average rate of change of f. It's going to be just some constant number. And then we need to figure out how many places the instantaneous rate of change, f prime, equals that constant value. So there's a few ways to do this. Average rate of change, there's a couple ways to do it on this one. Since you have the original function, you could do f of 1.565 minus f of 0, and then divide that by 1.565 minus 0, and that would be just fine. Another way to do it is to find the average value of f prime. Now, I'm going to do the second way. I mean, I have to find f prime anyway so that I can set it equal to whatever the AROC comes out to. So let me start by getting f prime. Using my power rule, that's going to be, let's see, 4 times 1/4 cancels, so we just have x cubed, minus 3, and the 3 here cancel, so that's going to be minus 2x squared, plus the 2 and the 2 cancel, so that's just 1x, and then finally minus 1/2. So there's our f prime. And now to find the average rate of change, one option I have is just finding the average value of this. So that's going to be 1 over the interval length, so 1 over 1.565 minus 0, times the integral from 0 to 1.565 of f prime of x dx. And let me see what that comes out to. So here I am in my y equals, and one benefit of using only f prime and not involving the f function at all except for taking its derivative is I only have to put one function in my calculator. So let me go back out now, and I'm going to do a fancy fraction here, 1 over, and this is just going to be 1.565, and then I'll multiply that by the integral, so math 9, from 0 to 1.565, and I'll have alpha trace y1 in here because that's where I just stored f prime. There is a dx, and if I press enter here, that's going to come out to this crazy value, negative 0.392. So I'm actually going to store that as a on my calculator and on the paper here just to represent it a little more quickly, but especially on the calculator. So let me do the store here, and we're going to do alpha a and press enter. So now I can pull that up whenever I want to. So at this point, I'm going to try to figure out on the interval from 0 to 1.565 how many places f prime of x equals a. So to figure that out, back in my calculator now, I'm going to go to my y equals again, and in y2, I'm actually going to put alpha a. So I'm basically graphing a horizontal line. I just want to find out how many places my derivative, my f prime, and my horizontal line intersect. But I need to set a window for this. So for my window, I'm going from 0 to, well, you guessed it, 1.565. We use that a lot here. And that should be a decimal, not a comma. So let me do zoom 0 now. And let's get the perfect window on this thing. Now, we're just trying to figure out how many places this intersects. And it looks like 1, 2, 3 places. We actually don't even need to figure out which places they are. We just have to count them. So this happens 3 times. So that means answer choice C. For this free response problem, the graph of this equation is given above for y values less than or equal to 11. You might actually be better off not looking at this graph for a little bit. It's known that the derivative of this function is given by 2x over 1 minus 5 sine of y, and the x-coordinate of point P shown on the graph here is 2. All right, so we want to write an equation for the line tangent to the graph at P. For that, we're going to need an x value, a y value, and a slope. We've got an x value. We need a y value to go with it. So the y value, it's kind of hard to tell. It looks like it's almost 5, but we need to find out exactly how much. So to do that, we're going to go back to the original equation, and I can at least say that for y values between 4 and 6, where this point P is falling, we can write the equation 2 squared, so just plugging in the x value 2 for x here, 2 squared equals, well, all this stuff on the right side of the equation. So I don't really know how to solve this algebraically. Fortunately, this is a calculator problem, so I'm just going to solve this on my calculator now. So to make this a little bit easier, I'm going to just use x instead of y in my calculator. I don't think using y would actually result in anything good anyway. And let's see, we've got the left half of the equation, the right half in y1 and y2. I'm just going to graph these at the same time and see where they intersect. And whatever intersection output, or yeah, whatever intersection x value the graph gives me, I keep in mind that that's really this y value I'm solving for. Now, I should pick a good window for this. I'm thinking for my window, since I'm pretty much guaranteed that this falls between 4 and 6 for the y values, for my window, let me just go to do a 4 and 6 for my input values. And then let me just do zoom 0, zoom fit. There we go. Zoom 0, there we are. So here's that horizontal line 4. Here's the right half of the equation. And there's only one intersection that we have to worry about on the interval from 4 to 6. It's right there. Let me do second trace, option 5, intersect. And let's just press enter 1, 2, 3 times. That gives us about 4.928 and some change. So there's my graph. There's a more zoomed out version of the graph that we end up with. Same deal though. And I'm going to actually store this as an A value on my calculator, just alpha A. So let me go back and do that because I'm going to need this value later. Let me quit out of here and let me press the store button and then alpha A. So now I can pull back that value whenever I want. And in my work here, I can now refer to this crazy decimal as just simply A, which will also save me a little bit of space. So that gives me a y value to go with the point, the x value, too. So I still need my slope. To get my slope, I just need to take the x value and the y value I have and plug them into this derivative they gave me. So let me do dy over dx evaluated at 2 comma a. So that's going to be 2 times 2 over 1 minus 5 sine of a. Let's see what that comes out to on the calculator. So there's what I'm entering on my calculator. And if I press enter, that's approximately 0.6798, which I'm going to refer to as m. I'm not going to store this on the calculator. It turns out I'm not actually going to need this value, but at least I don't have to write this over and over again. So now I have to actually write the equation of a tangent line here. So I'm going to use point slope for that. So y minus y1 equals m times x minus x1. So I'm going to have y minus the y value that I just found up here, which is a, equals my slope, which I wrote as capital M. This is a constant now that I can just use over and over again to represent the slope. And then I have x minus 2 in that parentheses. For this part of the problem, they want us to find y-coordinates less than or equal to 11 of each point where the graph has a tangent line that's vertical. All right, so basically with this derivative, we're asking where this derivative is undefined, which is to say the denominator has to have a value of 0, and the original function has to actually exist for whatever y values we find. So let's go ahead and figure out all the places where 1 minus 5 sine of the input number here equals 0. We'll do this on the calculator. So on my calculator, I'm entering 1 minus 5 sine of x in my y3, and I'm just going to graph, let's see, I don't want to graph these other things, so I'm going to unselect them. And I wanted to know where this equals 0, so I don't have to graph anything else. I just have to see where this graph touches the x-axis. I will adjust my window, however. So since I'm going from basically on this graph here, they said y less than or equal to 11, but presumably there's nothing underneath this little ellipse here. So let me do a window from -2 to 11, and that should cover me. So back on my calculator, we're going -2 to +11, zoom 0, zoom fit, and let's see what this looks like. So it looks like there's several places where we equal the x-axis here. However, although all of these places would give you a value of 0 for 1 minus 5 sine of y, not all of them are necessarily going to be on this graph here. For example, and here's the graph I just did on my calculator, if you look at this one, it looks like it's going through x equals 3, or actually this is y equals 3 because we're solving this equation here. And a y value of 3, if you look on this graph up here, and that's probably why they gave us this graph, the function doesn't even exist. It's not really a function. The relation, the curve doesn't exist there. So we're not going to bother finding this intercept because we know that's not actually on the graph here. Where else it would be on the graph? So this is between 0 and 1. It looks like that's going to exist. This one is between, let's see here, 6 and 7. So it looks like that's going to exist. Pretty much everything from a little bit above 4 onwards to 11 is going to exist. So we're going to find this spot on the far left, and then these two spots here are also going to exist and get to be included in our solution. So back to the grapher. Let's do second trace, option 2 for zeros. And where's my spider? There it is. Let's move it all the way to the left here. A little bit to the left of that first intersection, press enter. A little bit to the right, press enter one more time, and that's about 0.201 for that first y value. Again, we're solving for y values here. Now going back there, second trace, option 2 again for zeros. Let me move my spider a little further along. Now this intersection right here, remember this is not actually on the graph, even though it happens to be a place where this particular equation equals 0, it's not actually on the curve. So moving forward, we'll press enter once, and once to the right, and once again for this intersection. This is about 6.485, so we'll include that in our solution set. And then finally, we want to hit this last one right here. So second trace 2, and then moving my spider along, enter once to the left, enter again to the right, and then enter one more time to get 9.223. So that's our final y value. So these are the 3 y values that make your derivative undefined and also happen to be points on the actual curve. For this last part of the problem, the final boss battle for this one, they want the average value of the x-coordinates of the points on the graph in the first quadrant between y equals 5 and y equals 9. So this one looks kind of crazy in terms of, how are you supposed to find the average value of all these x values? The key on this one is to look back at the original equation here, where we have x squared equals all this stuff. So it would be very easy to solve this equation to get x by itself, and then we would actually have a function where if you gave me the y value, I could give you back an x value. Now, how would we get x by itself? Well, the only way to do it is to square root both sides of the equation. And you might be thinking, well, hold on a sec. Don't I get a plus or minus when I square root both sides of the equation? And you do. The key here, though, is that they said the first quadrant. So between the positive and negative root of all this stuff on the right side, we would just take the positive root because that would give us positive x values back, which would give us the stuff in this first quadrant. All right, so I'm going to define this x function here as f of y, just so I have something to easily refer to it as. And then this is going to just be the square root of that right side of the equation. So if I want to find the average value of basically this function here, this function of y, from 5 to 9, I'm going to do my average value setup. So 1 over the interval length, 1 over 9 minus 5, times the integral from 5 to 9. And here I'm going to get a little bit crazy. This is a function of y. So I'm going to put f of y in here, but I need a dy to go with it because y is my input variable here. And I'm just going to do all of this on the calculator now. All right, let's take a look at what I have in the calculator. We have 1 over 9 minus 5, integral 5 to 9. I've got this whole gnarly looking square root thing in my calculator. Notice that I'm using x though. You're allowed to do that. It doesn't really matter what variable you use as long as you use the same variable over here next to the d. And if I press enter on this, syntax error, ruh-roh. Let's see what the problem is. Oh, darn negative sign. I used the minus sign instead of the negative sign. Let me put a negative symbol in there and now press enter. There we go, 2.550. Man, that minus sign will get you every time.